And we'll go from current slide. All right. And we'll even turn on projector. Should have that on. And while that's coming up, actually, I think I'll pause this for just a minute. And here is it Joy? Ashley. Okay. I have a really good memory. It's just short, so I'll get around to it at some point. Okay. Let me make just a couple comments. I've had, and like I told you before, I have a full 30 minutes of office hours before this class meets, and sometimes I'm actually here a little before 8, so I have a few more. I did have someone in for questions this morning, but if you can't make it then, you can always ask questions during class. Okay? Or you can leave the room. Okay, no, okay, all right. You can always ask questions during class if you can't get here before 8:30 to ask questions. Now, the other thing with that because I can work any problem on the board too, and that way everybody, even people not here, can see that. So don't be shy about asking questions. Appreciate your questions. Okay. Any questions then before we get started? All right. Where we left off was talking about vertical asymptotes. We had introduced basically what they were. Here is the theorem that directs them. Okay. Let f and g be two continuous functions on an open interval containing some number c. So here's the interval. F and g are continuous on that interval. C is somewhere in the middle of that. Okay? Not necessarily the dead middle, but somewhere in between in the interval. If f of c is not equal to 0, okay, that's the requirement, but g of c is equal to 0, then there exists an open interval containing c. Okay, so f of x is not 0, g of c is, containing c such that g of x is not 0 for all the x's not equal to c, all the x's not equal to c in the interval. Okay? Okay. Then, okay, this is all the given, and there exists this. Okay? Then the graph of this function has a vertical asymptote. Man, that was a long way to get around to say that. So here's what the deal is. It's a rational function, a ratio of f, which is a continuous function on this open interval containing c, divided by g, which is also a continuous function on the interval containing c. F of x not 0, g of x is 0, g of c is 0. F of c is not 0, g of c is. Meaning that you have something not 0 over something that is, cannot exist. Cannot exist. Okay? There's the first part of it. And it also requires that there is an open interval containing c such that g of x is not 0 for all the other x's in that c. It can't be that g of x is just 0 everywhere, or even for a long period of time, or even a short period of time, more than just a point. It can't happen. This could be must be the only place in that interval where g is equal to 0. That's what this part is saying. Then this graph has a vertical asymptote at c. Now, there's one thing that they've left out here, unless I'm missing something. They should have said with no common factors. Because as I read this and think of it, they did take care of that. Because f of c cannot be 0. If it was a common factor, then f of c would be 0 too. So this says f of c can't be 0, but g of c is. So yeah, that eliminates the possibility of a common factor. And it also eliminates Ryan. No, it doesn't. It just says he's here. Okay. All right, so Ryan's here. Okay. Anyone else come in since I called roll? Well, it's also moving. The ball is already here. Okay. Good deal. Okay. Then this has a vertical asymptote to c. Why? Because because this is undefined. Not indeterminate, undefined at C. Okay? And that's the only place where G has a 0 there. So therefore, this is a vertical asymptote. Okay. That's in words. Let's check it out in practice. Here's example 2. And as I've mentioned to you before, this author has these various websites. One of these is larsoncalculus.com. You can go there and see an interactive version of this type of an example. Okay? Now, here's the problem. H of x, okay, here we go. Forget about this first part. Let's just focus here. Well, let me get my pen set up so we can focus better. Okay. All right. Let's look at this. Any problem, children, here? Any places you have to worry about? X cannot equal negative 1. And negative 1 will not make the numerator 0. Okay, the numerator is 1. It's always 1. It's not going to change. So that is going to guarantee, and that's the only value where the denominator would be 0. So you know this is going to have a vertical asymptote at x equal negative 1. So it says here, when x equals negative 1, the denominator here is 0. The numerator is not 0. Therefore, vertical asymptote there. Okay? Now, what were we supposed to do with that? It seems like they've done the whole thing for us here. So x equal negative 1 is a vertical asymptote. Now, I'm just going to tell you how I like to say that. I like to write it this way. X cannot equal negative 1. I mean, that's the truth. You cannot be negative 1. The book likes to say x equal negative 1 is where the vertical asymptote is. I like to say x can't be negative 1, therefore the vertical asymptote is there. So it's just my little way of saying it a little bit differently. Okay? Now, and I can't see anything else to do here in the problem except they do graph it. So that might not be a bad idea either. Okay? So let's graph this one. We'll erase this later. You know right off the top that x equal negative 1 is going to be the vertical asymptote, right? And when I go to graphic, and the book sort of does this too. No, it doesn't. I like to make the vertical asymptote red. A dotted line that's red. And that means the function cannot touch or cross that dotted line. Red means don't go there. Okay? So therefore, this is my vertical asymptote. Draw that in right off the top. And then at this point, you can just pick a few other points. One real easy one would be, give me a, try to check 2 rows here. Joy? Yeah. All right. Good deal. Anyone else come in since the call roll? You haven't heard me mispronounce your name or anything. Okay. Okay. Give me an X. Feel like a cheerleader up here. Second? 2. Okay. X equal 2. What will your denominator become? 6, right? And numerator stays 1, so 1/6. So at x equal 2, we're at 1/6. And I've got to get back to black. Okay. X equal to 1/6. That's awfully close. I don't have my Y scale here, but I'll put in a Y scale here somewhere. Okay. Okay. Something like that. Okay. Awfully close to 0, but not quite. Give me another X. Second? 0. Oh, my favorite. Okay. What would your denominator, what would your function become? 1/2, right there. There's your y-intercept, okay? Next, give me another x.
3.
Second?
3.
3, okay. What will your function become then? Second? 1/8, getting even closer to 0. Okay, I think I see what's happening down there, and I believe I know what's happening here, because it can't cross the x-axis. There's no zeros for this thing, so therefore it's coming here. It can't go down. Nowhere down it can go, then it will cross the x-axis, so therefore it must be going up, but it can't ever touch or cross the vertical asymptote, so it's going up like this. And when it gets here, it gets closer and closer and closer and closer to 0, but never gets to 0. Okay, that's a pretty ugly graph, but hopefully you see the general thing. So we know what's happening on that side. Okay? Now I could have made that easier, okay, if we had done horizontal asymptotes. Does anyone remember how to find the horizontal asymptote? That would have been in a pre-calculus type class or something. Remember how you do that? Okay. I was afraid of that. Okay. Go ahead and multiply this out. That'd be 2x plus 2 in the denominator. And then do the ratio of the leading terms. Well, the only term you got up here is 1, so it's 1 over 2x. What a horizontal asymptote is telling you is what happens in the long run as x gets very, very large positive or negative. With x it's very, very large positive or negative, 1 over 2x becomes 1 over 2 times a very large number, and that's going closer to 0. Here it's coming close to 0 from the negative side. Here it's coming close to 0 from the positive side, like we see right here. So the x-axis is actually your horizontal asymptote. Now I'm going to do something here. I'm going to draw that red too, just to be democratic about it. But there is a difference in a horizontal asymptote and a vertical asymptote. Anyone tell me what that might be? A vertical asymptote, the function can never touch it or cross it. Horizontal asymptote, yeah, it can cross or touch. It's just where it's going in the long run when you get very large x's, positive or negative. So that's why so it doesn't have to be red. You can cross it, but since I did the other one red, I did this one red too. Okay. The book didn't, but that's okay. So give me another x. We've taken care of everything to the right of -1. How about something to the left of -1? All right. Jalen?
Yes, sir.
Okay. There you are. All right, good deal. I think we're only missing Todd. Of all the regulars, he's the only one we're missing. And he did tell me he has to periodically take care of a younger sister who's somewhat disabled. So he may not be here, or he may be late getting here. Okay. All right. Give me an x to the left of -1. -2, one of my favorites, okay? So what happens if you put x equal -2 in that? Say again? -1/2, right about there, okay? Now, anyone, just with that 1 point, want to hazard a guess of where this function is going to go? Okay, it's got to go toward the horizontal asymptote as it gets bigger and toward the vertical asymptote as it gets smaller. There it is. And it may not be that sharp or whatever, but that's probably pretty close to what it is. Okay? Now, it could have crossed the horizontal asymptote. It won't. It can't cross the vertical asymptote, so that's why it's got to go downhill. Can't cross the x-axis, that would give you a 0, and we don't have any zeros. Okay? So that's what it's got to be. All right. Probably too much there. So let's clear the screen. Everybody got this? Anyone need it a little longer? Y'all are pretty excited about it, I can tell. Okay. All right. Then, oh, they draw the graph. Here we go. They drew the vertical asymptote there. Good first start. And then they, I guess, just picked some points, but they didn't tell you how. But all you really needed was 1. I would have done, I would have looked and seen that the x-axis is the horizontal asymptote. That's pretty easy to do, 1 over 2x. X is large is going to 0, so y is equal to 0 is the horizontal asymptote. And then once 1 point, 0 1/2, that would have been an easy one to do. That 3 has to go up this way, out that way. Same thing here, -2 1/2, negative 1/2 down this way, left that way. There we have it. They just threw it in magically, didn't tell you how they got those other points. All right, let's look at the B, okay? And I really don't like this. Why did they do all this for you, okay? You should have done this yourself, okay? Here's the problem. H of x is equal to x squared plus 1 over x squared minus 1, okay? What would be your first step? Don't read what my scribble is, okay? Factor what? Okay, really everything in sight, but the numerator is not factorable. So the denominator is factorable. How does it factor? Say again? X plus 1 times x minus 1. And what value or values then would you have to disallow in the denominator? Yes, negative 1 and 1. So we would say right off the top, x cannot equal negative 1 or 1. But we need to check and make sure neither one of these makes the numerator 0. Does it? No, numerator can never be 0. Okay? That tells you something right there. This function will have no zeros. There's no way you could ever make that numerator 0. Because you square any number in the world, positive, negative, whatever, is positive, or non-negative anyway, add 1 to it, and then it's got to be positive. So all of this is going to be above the x-axis. So obviously, neither one of those will make that 0. So those are vertical asymptotes. Okay? So let's go on and graph the function. Since we know it can't go positive, I'm going to put my x-axis way down there, and we'll do 1, 2, 3, 4, 5, 6, and negative 1, 2, 3, 4. Okay? Something like that. And then we'll do positive 1, 2, 3, 4, 5, 6, 7, 8. Okay, something like that. The axes should touch each other, but they don't. Okay. So, x equal negative 1, vertical asymptote, not very pretty. X equal positive 1, vertical asymptote, not too pretty. Okay. Now, at the same time, can someone tell me what the horizontal asymptote would be if it has one? Second? Positive 2, you said? Positive 0, is that what you said? Okay, didn't say that. Okay. All right. Actually, by putting in x equals 0 does tell you something. We should have done that before, but we'll do it now in a minute. Okay. The horizontal asymptote is the ratio of the leading terms. And what's x squared over x squared? 1. So the horizontal asymptote is y is equal to 1. Okay, there we've got that. Now, I think what maybe Ryan was hitting at is what happens when you put x equals 0 in? What does that give you? When x equals 0, what does that give you? Always. What's true about any place where x is equal to 0? You're on the y-axis, aren't you? What do we call that point? What?
Would that be the origin?
The origin's right down here. Okay? That's one point. But any point of a graph that's on the y-axis we call the y-intercept. Okay? Yeah, I just intercepted the passage. You didn't catch that. Okay? Yeah, it's funny. Yeah, like I could. Okay, I got that. Okay. So when you... Okay, you too. All right. Okay. Now, if you put x equals 0, what do you get?
Negative 1.
Oh, I sort of botched this up, didn't I? You get negative 1. I forgot. The function can be negative. The numerator can't be negative, but the function can, and I have it drawn way out of scale here, but negative 1 is your y-intercept. Okay, you're going to have to use your imagination here, folks. I'm not going to redraw this. Okay? Now, what we have to do from this point on is pick some other points. Give me a point. Any value. Second? 2? Is that here 2? Yeah. If you plug in a 2, you get, numerator becomes 5, denominator becomes 3. 5/3, which is 1 and 2/3. X equal to 1 and 2/3. Somewhere right about there. And if you put a negative 2 in, I bet you get the same thing, don't you? Because this is an even function. So you get right there. And I think we can tell what's happening in those two sectors. Here, as we're approaching the vertical asymptote, here approaching the horizontal asymptote. Here approaching the vertical asymptote, whoops, 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 shooting across. And here approaching the horizontal. Now, the only thing we're missing is what's happening in between. We know one point down there. But what we don't know is whether it's opening upward or opening downward or coming down like this or up like this. We just know it passes through here, except for this. We already notified ourselves the numerator cannot be 0. So therefore, it doesn't have a horizontal asymptote. I mean, a horizontal intercept. Okay? It does not. There is no x-intercept. So this has to be opening downward. And this is where you use your imagination, folks. It's going down like this and down like that. Approaching the vertical asymptotes but never touching. So it sort of looks like a, kind of like a secant function there, you know, going down like that, only a negative secant function, going down like that, approaching the two vertical asymptotes. Get an idea? If you look in the book, you'll see a little bit better drawing. Not much, but a little bit better drawing than mine, okay? Any questions on that? Okay, so let's see how they do it. I'll erase my scratch here. And, yep, same reasoning. We can see that the denominator is 0, x equals -1 and +1. The numerator is not equal to 0 there. The numerator is always positive, so it will not have an x-intercept. And so those are your two vertical asymptotes. By picking just one more point, and +2 and -2 gave them to us, you know where you're going in those portions. They didn't draw the vertical horizontal asymptote. That would have made a lot more sense if they had x equal or y equal to 1 from the ratio of leading terms here. That would have helped our graph some. Then all you have to do is pick. You could have picked a point here, or you could have reasoned it out. You know there's no zeros, so this has to be going downhill on both sides. So there's your function. Make sense? Now, didn't say you got your y-intercept by plugging in x equals 0. All right. Oh, why do they do this? Okay, they've drawn the graph, given everything away. Just pretend you didn't see this. Okay, I'll stand in front of it. Here's our function. H of x equals cotangent x. If I ask you to graph that, probably the easiest way would be to first break cotangent into cosine over sine. And y'all knew that, didn't you? Yes, of course you did. Okay. Now, what is the first feature of the function that you better identify? Say again? Where the denominator is 0. That's what you said, right? Absolutely right. Okay? Now, where is the denominator 0? Where is sine 0? At what values? All your pi's. 0, pi, -pi, 2 pi, all your pi's. So there, put your, and they didn't do this one, but y-axis is 1, and every pi. Okay? Those are your vertical asymptotes. Get them in there. Can't touch it, can't cross it. Okay? Then after that, the issue is, what is the numerator doing? Well, where is the numerator equal to, let's say, 0? Where is the numerator equal to 0? Where is cosine equals 0? At the half pi's. So there are your zeros at all the half pi's, in between those two pi's. Okay? Now, you can't plug in x equals 0 to get a vertical asymptote because it doesn't exist. Sine is 0 there. So that's a vertical asymptote there. So no vertical asymptote, vertical intercept, no y-intercept, but we got all the x-intercepts in there. There is no horizontal asymptote, okay, because the ratio of the leading term. This isn't a polynomial, so you can't use that there, okay? Now, the next thing, and this is how I do it, and it's just as good as any. I know what's happening in the first quadrant. Cosine is positive, sine is positive, right? So cotangent is positive. You got a 0 there, a vertical asymptote here, has to be going uphill that way, right? No choice, okay? Because it's positive in the first quadrant, okay? What about the second quadrant? What is cotangent there? Negative. All students take calculus. You remember that one, or chemistry, or whatever, all state technical college, whatever you want to call it, is second quadrant, tangent and cotangent are negative. So it has to be going down and go from there. Okay? Now that gives you everything between 0 and pi. That is the period for cotangent. So just take this and replicate it in every interval. Just draw that same graph in every interval. It's positive in first and third quadrants. That quadrant, this is the same as the third quadrant. That's, it repeats itself every time. So even with trig functions, do your vertical asymptotes, find your zeros, find which are your x-intercepts, find your y-intercept if there is one. There's not one in this problem. And then pick a few points. If you can't figure it out from there, and go from there. Any questions? They did it all on one screen here, and it was really hard to wipe all that out. Okay. No questions? All right. So the graph of the function has infinitely many vertical asymptotes, all at your n pi's. Okay? Where n is any integer, positive or negative. Okay. So I know you like to do. Oh, they're skipping examples 3 and 4. So let's go back and do 3 and 4. Okay. Goodness gracious, they don't give it. There's one with some room. Okay. Example 3. Determine all the vertical asymptotes of the graph. And that's all they're asking for. Vertical asymptotes, well, they're going to ask you to draw it anyway. Okay. Of the graph of h of x is equal to x squared plus 2x minus 8 divided by x squared minus 4. What's a good first step? Factor. Factor everything in sight, numerator and denominator. Will that numerator factor? It may not be factorable, will it? We're going to have to start with x and x, and then because the sign of the last term is negative, that's going to be a plus and a minus. Are there any two numbers that multiply to be 8, 4 and 2, and which one's which? Which one's positive, which is negative? Positive 4, negative 2. Very good. How about that denominator? X plus 2 times x minus 2. Now, if we had not factored everything in sight, okay, numerator and denominator, if we had just factored the denominator, we may have guessed x equal 2 and negative 2 and x equal positive 2 are your two vertical asymptotes. Not so here, because x equal 2 would make your numerator 0 as well. That can't happen. So by factoring, we see these go out. But a warning, x can still not equal 2. It can't, because that would make your denominator 0. Even though it's indeterminate, it would make it 0. It just means it's not a vertical asymptote at x equal 2. It can't equal 2, but it's not a vertical asymptote there. There is a vertical asymptote at x equal negative 2. So let's draw it in here. There's your vertical, I'll put a few more points here, something like that. I don't do very even points, obviously. Oh, you're making fun of me, aren't you? Okay. Never mind. I'm not hurt by it. Okay. Here's the vertical asymptote. X cannot equal -2. Now, I'm going to do something else here. I'm going to do this, okay? That's not part of the graph, but that's to remind myself it can't equal net +2 either. It's just not going to be a vertical asymptote. This is my little thing. You never see a book do it, but, you know, I like to do that. Okay. What's your horizontal asymptote? That's the ratio of your leading terms. That's going to be 1. Let me get back to black. Okay. That would be ratio of leading terms, and that's 1. So y equal 1 is your horizontal asymptote. That's helpful. Get out of there. Okay. How about zeros for the numerator? That would give you zeros for the function. Well, we obviously see, we know x can't be 2, so that one's out. But this one will give us -4. So -4, woo, barely made it here, but there it is. That's going to be a 0. I know what's happening there. Don't you? Here it's going to the horizontal asymptote. Here it's going to the vertical asymptote. No choice. It's not, you know, just can't happen any other way, I don't think. Okay? Now, one really easy thing we haven't done yet, and what was that? Did the horizontal, the x-intercept. What have we missed? Y-intercept. How do we get that? X equals 0. So I'm going to just cover all my zeros, and what do you have y to be? It's what? It's -8 over -4, which is +2. So there's your y-intercept at +2. Guess what? We know where this is going to. It's got to be going up this way for this one and down this way for that. Hey, didn't have to do a single test point. Just your intercepts on this problem won't always happen this way. Oh, but I blew it, didn't I? Oh, y'all weren't watching. Hole in the graph right there because it can't equal +2. That's a pretty ugly hole, isn't it? Let me see if I can make that a little bit better. Well, I erased everything. That's a lot better, didn't you say? I thought you did. Okay. Sorry about that. I'm not going to redraw it. So, if you got your books, you'll see there's a hole in the graph right there. Otherwise, they did draw the horizontal asymptotes. I don't know why they don't, but we made it a lot easier to see. There's that hole in the graph. X equals 2, or X can't equal 2. Make sense? Any questions? All right. Let's try example 5. That's why I erased the graph so we could do 5. Okay. I was just looking ahead, being psychic. Okay. Now, we're jumping back to limits again. Ew, I was hoping we were through with these. Okay. It says find the limit as x approaches 1 from the negative side of x squared minus 3x over x minus 1. Okay? And they also want us to find the limit as x approaches 1 from the positive side of the same thing. X squared minus 3x over x minus 1. All right. Now, my feeling on this is to just plug it in and do it algebraically. Because I really don't care for the graphing that much. I mean, they're beautiful and all that kind of stuff. I just, more time. Okay? So, what would happen? First thing you usually try for a limit is Glade. Plug it in. So what happens? Well, you know what happens. that goes to 0. Does that go to 0? If it does, then we may have hope here for a limit. Does it? What does that go to? Is that a -3? No, -2? Yeah, -2. Okay? So that's going to -2, that's going to 0. Well, even if that's not quite 1, let's approach it from the minus side here, then this means this is going to be something a little bit less than 1. So that makes the denominator negative, right? And the numerator negative, right? So that's going to be positive. So it looks like to me this has no limit, okay? It's an undefined state. So what the book likes to call this is going to an infinity. That would be going to a positive infinity. Doesn't it appear? Okay, because as x is approaching 1 from the negative side, then this is negative, right? And then we already determined that would be -2. And negative over negative, yeah, is positive. So this would be approaching positive infinity. Because x cannot equal 1, okay? So there is no, that's a vertical asymptote. So this is going high there. Now on this side, where you're approaching from the left-hand side, same numerator, so that's still going to be a negative, what do we say, 2. But this now is something greater than 1. So something greater than 1 minus 1 is going to be positive. So this will be 2 over, or -2 over something that's slightly positive. That's going to -1. So this would be approaching negative infinity. Okay? Now, how do we verify that? They're showing it on the graph. Okay? So let's do our graph. Okay? There's our 1, and we know it. Let's do all our tick marks. They're really lousy. Okay. And x equal 1 is our vertical asymptote. Now, is there a horizontal asymptote? Really? What? You don't have to have a horizontal asymptote. You don't have to have a vertical asymptote either, but let me go back to black here. What's the ratio of leading term tell you? That's going to be x, right? And is x is very large positive or very large negative? It's going very large positive. No, there is no horizontal asymptote because this is unbounded. Okay? If the numerator has a lesser degree than the denominator, that's going to 0. If they have the same degree, it's the ratio of the leading coefficients. But if the numerator is greater degree than this, it's going to infinities. So no, this has no horizontal asymptote at all, because the degree of the numerator is greater than the degree of the denominator. Now, do any of you remember what this does have? And I didn't cover it much when I did pre-calculus algebra because we just didn't have time. This has what they call a slant asymptote, because the degree of the numerator is exactly 1 degree greater than that of the denominator. So that means you can do what they suggest is do a division. Do y'all remember how to divide polynomials? One of your favorite pastimes? You play that game all... No, you probably don't. Okay. So what we do, dividing by the denominator, since that denominator is the x minus 1, we can just divide synthetic division by 1. Okay? I think this is how I do it. And I put it in the numerator, the coefficients here. That would be a 1 minus 3 And then you have to put in a 0 because that last term is 0, right? You have to account for every term. Skip a line, draw a line, bring down the 1. 1 times 1 is 1. Add -2. Multiply -2. Add -2. You're sort of stuck. So that has a sort of forget about that for a moment. What this leaves you with, if you do a division here, this would be x minus 2. What the x minus 2 is a straight line with an intercept of 2. Okay? So and a slope of 1. So let's sort of draw that in, and this is going to be really hard to do with my irregular points there. But it would be, get out of there. Okay. It would be something like, why is it doing that? My pen has disappeared. There we go. Okay. This is approximately a slope of 1. Okay. That, I'm sorry, I probably should have done it in red. That is what we call a slant or oblique asymptote. Okay? Now, let's pull back for a moment here. Okay? And do this. And you notice here that when x is negative, forget about it. We'll come back to that. Okay. What we didn't pick are some of our good points. What were the zeros of this function? Where are the x-intercepts? What did you say we should do to this? Probably every one. First thing we should do is factor everything inside. The denominator is not factorable, but numerator is. What would that be?
Factor out of x.
Yes, that would be x times x minus 1. So what would be your zeros? X equals 0 and x equals, or x minus 3. Whatever I said. X equals 3. Those are our two zeros, right? 0 will make that 0, and 3 would make that 0. 9 minus 9 is 0. Okay? So 0 and 3. So there is, whoops, finish with that color. Okay? 0 and 3. All right. You know, I botched something here. I botched it badly, and y'all let me get away with it. Shame on you. I'm wiping out way too much here. Okay. You let me get away with this, and it was just really pathetic. What is wrong with you people? Okay. X minus 2 is a straight line with a y-intercept of -2, not +2, right? Okay, what were you saying? Hey, you got that wrong, guy. Okay, you can say that. It's okay. Don't call me guy. My name, never mind. But here is that, and let me this time do it in red. Here is that slant asymptote. Now this is making a lot more sense. Okay. I think at some point, where's my pen? There it is. Okay. Where's my zeros? There and there. Now this makes sense. Here it's approaching the vertical asymptote. Here it's approaching the slant asymptote. Here it's approaching the vertical asymptote. Here it's approaching the slant asymptote. There's your function. And you see there is no horizontal asymptote. There's a slant or oblique asymptote. Okay? That only works when that degree is 1 more. If that had been a cubed here and that x, don't even bother. You know, it won't tell you anything. Only when that is exactly 1 greater do you have a slant asymptote. It's not with pen. Yeah, it's sort of like an asymptote anyway. Okay? And by the way, the y-intercept is also 0. So here we have the graph of this. And as you see, as x is approaching 1 from the negative side, it's going to positive infinity. As x is approaching 1 from the positive side, it's going to negative. Sure that fits. And what I was going to say before, if x is going negative, infinitely negative, then this is acting like a linear function because it's approaching that function x minus 2, so it's going negative this way, positive, infinitely negative, infinitely positive, because that keeps on happening. So yeah, everything sort of fits. Make sense? Not really, huh? No, say yes. Okay. All right. Now, that was example 4. Probably way more than what you wanted. Okay, all I asked for was the infinities, but I wanted to show you how they got the graph, because they did do a graph. So I think we're through with that. So, well, I don't even have to erase this. I can just move on to, now we're ready for vertical asymptotes, theorem 1.15, properties of infinite limits. All right. Let C and L be any two real numbers, any real numbers in the world. F and G are functions such that the limit of F as x approaches C is positive infinity. And the limit of G as x approaches C is L. Okay? So here, F has no limit. It's going infinitely large as x is approaching C, and it doesn't say from which side, so I would have to assume from both sides, because they say that as x approaches C, that F is approaching positive infinity. They don't say right or left, they just say C. But G is approaching L, so it does have a limit somewhere. So the sum or the difference, if that's going, as x is approaching C, if that's going to infinity, no matter what L is, that's still going to infinity. As if this is going to positive infinity and you're subtracting L from it, guess what? The difference is still going to positive infinity. The product, okay, as x is approaching C, is going to be, this is going to infinity, that's some limit L, that's going to a positive infinity, if that L is positive, okay? Because positive infinity times a positive L is going to be a positive infinity. But if this L is less than 0, meaning negative, then that would be positive infinity times a negative number, that would be going to negative infinity. Why don't we just say these limits don't exist? But they don't like to say that. Now the quotient. Most of the time we put F on top. This time we put G on top and F on the bottom. If F is going to getting infinitely larger than G is just fixed, then this is a number. Even if G is 4 million, but it's constant. If L is 4 million, okay, then as F gets going to infinity, that gets up to 4 billion to 400,000 trillion or whatever. 4 million over that is getting closer and closer to 0. Anytime the denominator is increasing without bound, the numerator is not, that's going to 0. Okay. If you flip them, that would be positive infinity. Well, yeah. It would be the same thing as this. Positive infinity if L was positive, negative infinity if L was negative. Okay. Now it says similar properties hold for one-sided limits and for functions for which the limit of f of x is x approaches C is negative infinity. You just have to play with your signs. And frankly, to me, if it's going to infinity, that limit doesn't exist. So why even mess with this saying, I don't know, but they like to say it. So let's do this one. Example 5. The limit, all right, the limit as x approaches 0 of 1 is what? 1. 1 is a constant function, right? And no matter what x is approaching, it's still 1, okay? So that was one of those early limits we did. The limit of a constant is a constant no matter what the x is approaching, okay? It's just that constant. Okay, now the limit as x approaches 0 of 1 over x squared as x gets closer and closer to 0, either from the right or from the left, 1 over x squared is getting to be x squared is going to be a very, very, very small number, positive number, because whether it's positive or negative, you square it, it's going to be positive, and it's going to be getting smaller and smaller and smaller, and 1 over a very tiny number is going to infinity, okay? Try it. I mean, 1 over 0.1, that's 10. 1 over 0.01, that's 100. 1 over 0.001, that's 1,000. Or negative side either. Only these are squared, so they're always going to be positive. So 1 over an infinitely large number, an infinitely small number, getting closer and closer to 0 is going to be positive infinity. Okay? So therefore, big deal here, this limit is 1, that limit is infinity, add 1 to infinity, you're still an incredibly large number. So that's going to be infinity. I would say the limit doesn't exist, okay? Okay. This one, all right, okay. This is a whole new problem. Forget any of that. The limit as x approaches 1 from the negative side of x squared plus 1. Well, what's that? You tell me.
2.
Yeah, because this would be 1, and that would be 1. 1 plus 1 is 2. High level math today, right? Okay. How about this one? The limit as x approaches 1 from the negative side of cotangent of pi x. What was cotangent in general?
Sine of cosine.
Say again?
Sine of cosine.
No, that's tangent.
Cosine.
Cosine over sine. And as sine is going, as x is going close to 1 from the negative side or positive side, sine of pi x, this would be pi x from the negative side, sine, 1 pi from the minus side, that's, the sine would be going to 0, cosine over sine would be going to infinity. But it would be going from the minus side because the cotangent, remember, does like that. So it's going from the negative infinity. Okay? Now, because this is a fixed number, 2, and this is going infinitely large negatively, who cares what it's going, then the limit as this quotient here, if this is going to an infinity, positive or negative, that's going to 0. If your denominator is getting bigger, the numerator is fixed, which it is, then you're going to 0. Okay. So in this case, I guess, just because something doesn't have a limit, if it's in the denominator, that will send the whole expression to 0, as long as that numerator is not going to infinity. All right, here's another one. I hope we know that. Limit as x approaches 0 of 3 is 3, okay? And the limit of cotangent x as x approaches 0 from the positive side is? Yeah, infinity, and positive infinity, because that's cosine over sine, and sine as x is going close to 0, is going close to 0, so that would be positive infinity. So then if you do the product of those two, 3 times an infinitely large number is an even larger infinitely large number. So, yeah, I don't know why I mess with that. Is there a d? Yes, there is. What's the limit of x squared as x approaches 0 from the negative side? 0, yes. How about limit as x approaches 0 from the negative side of 1 over x? Say again? Negative infinity, because it's approaching zero.
So on the test, do you want us to write the infinity or can we write those negatives?
Think through the whole problem, everything they're asking. See, you couldn't just stop here and say infinity because this one's in the denominator, so that would make this one go into zero. But when it's up here, let's see what it's asking here. It's the sum of these two. I would be perfectly happy with you saying that does not exist. And I don't know that it really matters that it's going to a negative infinity, not existing down there rather than not existing at positive. I don't really care. So frankly, I don't care on those. This one, don't just write because this is going infinitely large. That's in the denominator. That's dropping that to zero. So you have to think through the whole problem, not just the individual pieces. Okay. Now, that was example 5. And that was the last example in the section. Okay. So let's go. Homework exercises here. Do either 3 or 5 or both. They're both at Calc Chat. 3's at Calc View. 7 or 9. They're both at Calc Chat. 7's at Calc View. Any of the odds 11 through 15, they're all at Calc Chat. Any of the odds 17 to 31, they're all at Calc Chat. 25's at Calc View. 33 or 35, they're both at Calc Chat. 33's at Calc View. 37 through 49, they're all at Calc Chat. 41's at Calc View. 51's at Calc Chat. 53's at both Calc Chat and Calc View. You can explore doing either 55 and or 57. They should both be at Calc Chat. Now it's suggesting you might need some type of graphing utility to do this, but you can see if you can figure it out without one if you don't have one. 59, 61 you should be able to do. 63 looks like a reasonable problem. The B part, they say you need some type of graphing utility. There's some true faults. 65 and or 67, they should all be at Calc Chat. And then there's 69's a problem. You could probably do. 71's a proof. You can do it if you'd like. And 73 and or 75 are a couple of more you could do if you'd like. They all should be at Calc Chat. Now, that's it for section 1.5. There are some review exercises here if you feel like you need a little extra practice on some of these. These go pretty much by the section, so I'll let you decide. The odds are at Calc Chat. The evens, there is no Calc View on these. So you can do 1 if you'd like, 3 if you'd like, 5 if you'd like. Either 7 or 9, or both. Any of the odds 11 through 27. Either 29 or 31, 33 or 35, 37, any of the odds 39 to 49, 51, 53 to 57, 59, any of the odds 61 to 65, 67, 69, 71, any of the odds 73 to 77, 79 to 87, and then there's a problem number 89. Looks like a pretty interesting one. There's this little thing on problem solving. If you're interested in that, you can pursue that. And that finishes the chapter. Okay? So what I'm going to do is close out. Any questions before we go? Okay? I'll discharge what we had, get out of this, and go to 2.1. Now, is this a reasonable break time? We've been at it, what, about an hour and 15 minutes, right? Seems longer, doesn't it? No, you don't answer that question. Okay. I usually like to go at least an hour and a half, but we could take a break now if you'd like one. Would you? You would? Okay. why don't we take a break here? So I will stop right here. I'll set it up so when we come back, we'll be ready to go. I'll turn off the the brakes, right? All of you were here before. Okay. Now, let me reiterate a few things I've said and maybe mention something. I can't remember if I said it or not, but all right. You have 1 week to complete the test, though I give you more time if you need it. But, I give you a week. 2 reasons to give you a week. One reason is you always have a day to ask questions. If there's something on here you don't understand what I'm going for, what it do, that kind of stuff, you can ask a question. Okay? That'll be next Monday. Okay? Second reason, you always have a weekend to work on it. That's coming up. Okay? Now, I can't remember if I told this class this or not. I told at least one of the classes. I don't remember which one. But let me say it now. Okay. All things are on one piece of paper here. You can't work this on this one piece of paper. I don't have a magnifying glass big enough to be able to expand that so I could read it. Okay? So you'll probably need scratch paper. Okay? I don't think there's any graphing on here. So I don't think you need graph paper. But please, now you can use the back if you want to use the back. That'll be fine with me. What was that? Okay. But you'll probably need some additional paper. Now, here's the rationale for what I'm about to say. I've received some pretty serious griping that I give take-home tests from other faculty members because they don't like that idea. I kind of do like that idea. So what I sort of a compromise type thing, you need to show your work. If you just fill in answers here, the maximum score you can get, if all those answers are right, is 50. Okay? That's all you can get. If you don't show the work for a problem, you lose half the points on that problem. And there are approximately 10 points each because there's 10 questions in it. There's 5 gone from every problem. So please show your work. That's why I say you will need, my guess, you will need additional paper. Lined paper, unlined paper, I don't care. As many pages or as few pages, I don't care. Just make it pretty legible. I've got to be able to follow your logic. Now, if you like to skip steps, as long as I can see what you're doing, that's fine. But it's a good idea to put in all the steps so even an old slow mind like mine can maybe follow what your logic is. Is that understood? Please show your work. Otherwise, you're going to lose at least half your point. If you get a wrong answer and don't show your work, you're in pretty serious shape then. Okay? So show your work. Now, let me also say this. If you show your work and get a wrong answer, but your work is heading in the right direction, I love to give partial credit. So you see, before in these classes, people say, do we have to show our work? I say, well, if you don't show it, I can't give any partial credit. I thought that was incentive enough to do it. It may not be. So now I'm requiring you to show your work. And if you are heading in the right direction, get a wrong answer, you'll get as much partial credit as I can dig up to give you, okay? You won't get it all right. If it's a wrong answer, it's a wrong answer. But I will give partial credit if you're heading in the right direction. All right, any questions on that? Okay, I did want to make that clear. Now, I wanted it on the recording so people listening at home will know, number one, I passed out the test, and number two, what their parameters are when they come to pick up the test. All right, any questions, chapter 1? Go over it this weekend. Do as much as you can. If it's just a piece of cake and you finish it, you can turn it in Monday if you'd like. But that gives you Monday to ask questions. Now, if you still need more time after you've asked questions on Monday, then I'll give you more time. I just want them all turned in before we get to chapter 2 test. Because I don't want you making the same mistakes on chapter 2 you did on chapter 1 because you didn't turn in the chapter 1 test, and now I have to correct them twice. That's just extra work on me, and you get worse scores, a lose-lose situation all the way around. So get your test in before we get to chapter 2. So you can see if you are doing anything wrong and make those corrections before before you do chapter 2. All right, any questions? All right. Chapter 2 is then on differentiation, the first big part of calculus. Limits were just leading up to differentiation and also integration. We're going to use them in both, but here's differentiation. 2.1 is talking about the derivative and the tangent line problem, and if some of this looks familiar, it ought to, because we were talking about this before with limits, but now we're doing the derivative and the tangent line problem. Here are the objectives for this section. Find the slope of the tangent line to a curve at a point. Okay? Slopes usually are given from 2 points. Now we have to find the slope at a single point. So our good old slope formula, we're going to use it to some extent, but in a limit sense. We'll use the limit definition to find the derivative of the function. Yes, that sounds like a lot of fun. And we'll understand the relationship between differentiability and continuity. And there is one, and there are two pretty linked concepts, but not quite the same concept. Okay? So let's first look at the tangent line problem. Like I said, you'll probably recognize this from before. Now, there's a pretty little picture on the page of an outstanding looking mathematician. In fact, one of the greatest minds I think that's ever walked this planet was Sir Isaac Newton. Okay? 1642 to 1727. Boy, he had a pretty good lifespan there. That's what? 85 years old back in those days? That was pretty good. Especially considering the fact he was a preemie. They didn't even think he was going to live. Okay? Back then, preemies had a pretty bad chance, but he did live. Okay? He grew up without a dad. His dad died before he was born. Okay? So he never knew his father. Another, not the most positive things. He, fortunately, was incredibly brilliant, but not everybody recognized that. His mother wanted him to farm. He was not a very good farmer. He spent all of his time watching apples fall off the tree. No, I'm just kidding. That's sort of old story. But he had an uncle, I think, that sort of took him under his wing and got him into one of the great universities. I think it was Cambridge, but it was either Oxford or Cambridge. I think it was that. But he was so poor that he had to basically be a servant to the richer students to pay his tuition. He, I guess, washed their clothes, shined their shoes, polished their brass, delivered their food. I don't know what all he did. It wasn't a very easy road. But academically, in about 3 years, he had surpassed all of his teachers. Okay? He was eating up everything they fed him and going beyond and thinking beyond what they did. The head guy in the math department, as soon as he graduated, he said, "Here, you take this chair." You know, the head of the math department. Okay? The Lucasian chair of mathematics at, I think it was Cambridge University. Say again.
Biography that you're giving us, so the biography that you're giving us about such a story, do you want that in the research paper?
Yeah, you could choose Newton as a research topic. That's
The biography that you're giving
yeah, something like that. Yeah, if you have to look it up. Don't go by what I say. I could be making all this up. You don't know. I'm worse than the internet. Okay. Okay. So you have to look it up and find your own sources, right? You wouldn't trust me, would you? Oh, that's a tough one to answer, isn't it? Yeah. All right. Okay. So, no, you have to find your own sources. I'm just sort of making it enticing so you say, hey, this may be interesting looking into this guy, maybe. But if you'll notice this little blurb here, his name is here, so you could do his biography. In addition to developing calculus, it says his work in calculus. He developed calculus from scratch. He made revolutionary contributions to physics. You could also attack one of those, including the law of universal gravitation. That's the apple tree story, you know. No one had even come close to explaining why gravity exists. He did, okay? His 3 laws of motion, optics, light, I think he even did a little bit of photoelectric effect. I mean, way beyond his time, okay? And developed a whole new branch of mathematics, calculus, from scratch. Well, pretty much from scratch. He built on other people's things. That's why he went to university, so he could hear everything that had been done in the past that he went by. And one of his most famous quotes are the ones I like best. And he wasn't known to be a very humble guy. I mean, he had really humble upbringing, and that probably made him a little bit of an irascible type personality. But someone asked him one time, how is it that you look at these things, apples falling off trees, motion, stuff like this, and you can see answers where nobody else could? How can you see these things that no one else? And he said, if it seems like that I have seen further than people before me, it's because I was standing on the shoulder of giants. So in other words, he took every one thing that had come before him and then stood on their shoulders and could see just a little bit further. Pretty great quote in my mind, okay? Incredible individual, okay? So if you think about writing on Newton, his life is one possibility. Is that what you're asking? Another would be how he developed calculus, or something to do with that. What he did in physics, universal gravitation, optics, light. I mean, just all the things, 3 laws of motion. There's just a ton of different topics, almost enough for everyone in the room to have a different topic if all you wrote on was Newton. I'm not saying that you should. There was also sort of the downside. Like I said, he wasn't the most agreeable person. He had feuds with people like crazy, notably Gottfried Leibniz, who we'll be talking about shortly, because Leibniz also developed calculus. But boy, did they go after each other like cats and dogs, because Newton was convinced Leibniz had stolen his idea and rushed to publish it. See, that was one thing about Newton. He didn't want to publish anything until he was absolutely certain he had dotted every I, crossed every T, and everything was in order. He did not take well to criticism, so he wanted his idea to be perfect, perfectly done. In his great mind, that was a high bar. So he took years to work on something. Leibniz published pretty quickly. He also made a lot of errors, a few errors, and then he'd have to retract it and redo it. And he was a bright guy, but Newton was convinced that he took Newton's ideas and rushed out and published them ahead of him. And they fought for the rest of their academic lives. What a waste to have these two great minds not doing new things, but fussing at each other. So there's other potential paper topics there too. Anyway, let's move on. Calculus grew out of 4 major problems that European mathematicians were working on during the 17th century. One of these was the tangent line problem. Okay? We'll be talking about that mostly in this section. The velocity and acceleration problem, which is sort of the tangent line problem in one sense. Okay? We'll see that too. Newton really was focused on that because he was physically oriented, not just pure mathematics out and pie in the sky type stuff, but solving practical problems. The minimum and maximum problems, I'm pretty sure that Newton was tackling that as well, and the area problem, which is basically going to get into integration. So we're not even going to touch on this for a couple more chapters. Okay? Each problem involves the notion, good old limit, okay? And calculus can be introduced with any of the 4 problems. We're going to start with the tangent line problem, which you'll find is very close to the velocity and acceleration, and then we'll move to max-min, okay? You could have reversed the order, but this is sort of how it was developed, so that's how we're going to proceed. What does it mean to say that a line is tangent to a curve at a point? Okay? Centrally, this means the problem of finding a tangent line at a point boils down to the problem of finding a slope when all you got is 1 point. A slope when you got 2 points It's easy. Rise over run. I mean, we know that way back from early mathematics. That's pretty easy. But when you got 1 point, how can you know the slope there? Okay? You don't have but 1 point to go on. Okay? So that's what we're going to be doing. That's where we use limits. Okay? You can approximate this slope by using first a secant line. Because a secant line, see, here's the curve. There's the point x equals c. There's the alpha c here. This is the one we really want to know the slope at that point, but we don't know how to find the slope at a single point. So let's pick a point nearby. Let's just go a little distance away, call that a delta x. In other words, change the x just a little bit to here, and that will give you a new point up here, alpha c plus delta x. So at this point, this was c here, c plus delta x is here. This will then be alpha c plus delta x. Okay? Now we got our good old rise over run problem. The difference between the y's, alpha c plus delta x, and alpha c, that's going to be your delta y, and the difference between c plus delta x and c, that's going to be your x. The c plus delta x minus c, the c's go out, and that just leaves you delta x. Yeah, that's the length right there. So this is now what we're considering. The change of y over the change of x. Okay? So, that's not going to give you the tangent line. That will give you an approximation to it, but not exact, because that obviously is a tangent there. So, what do we do from there? Okay? If c, alpha c is the point of tangency, that's the one we're really interested in, and this c plus delta x and alpha c plus delta x is some point further up the curve, is the second point on the graph, the slope of the secant line through those 2 points is given by substitution into the slope formula. The change of y over change of x. Here's your change of y. Y is equal to alpha of x. Okay, so this is the y at the second point. Here's the y at the first point. And then these, that gives you this right here. There's the slope of the secant line. Okay? Done. Okay? The right-hand side is a difference quotient. Hey, remember that from pre-calculus algebra? Difference? Oh, you don't. Okay, you were asleep. Never mind. Okay. So that was the difference quotient from back there. The denominator, the delta x, is the change of x. The numerator is your change of y. Rise over run. Just like before, and we've said it a dozen times, they just keep repeating it. They think it's important. All right? So, what do we do then? To obtain more and more accurate approximations of the slope of that tangent line, let's let the second point get closer and closer to the point of tangency. In other words, here's your... Okay. They look like the... Well, no, they're two different graphs. That's what they're doing here. Okay? Here's the point that we're really interested in. There's that secant line. So let's let this point get closer and closer down here. So your delta y's are getting smaller as your delta x is getting smaller. And the delta y is getting smaller. Okay. And then suddenly are in a limit, then they could coalesce onto the same point. So if this limit exists, then we can find that slope of the secant line. Same thing over here. This is a more, I see what they're doing. Here's the point of tangency on this one, okay? A little bit different curve, but who cares? Different point of tangency. This time we're going to let the delta x come up from the left-hand side, okay? Getting closer and closer to that, and you see the delta y over delta x. Now, notice here, folks, this is important. The delta y is changing as delta x. It's getting smaller, they're getting smaller. They're both approaching 0. 0 over 0, indeterminate form. If the limit exists, we have the slope of the tangent line. Now, if that limit doesn't exist, hang it up, Jack. There is no slope of that tangent line. Undefined, or something. So you see we have a 0 over 0 indeterminate form. We're not just dividing by 0, you're dealing with an indeterminate form. Does that make you sense? Okay. Whether it is or not, we're moving on. Okay. Here's the definition of the tangent line. with slope m. If f is defined on an open interval containing some number c, and if the limit as delta x approaches 0, or delta y or delta x is this limit, which is exactly what we said it was, alpha c plus delta x minus alpha c over your delta x, that's the slope of the secant line, and if you let that delta x get smaller and smaller and smaller from either direction, as that's approaching 0, if this limit exists, that is the slope of not the secant line anymore, but the tangent line. If that limit exists, then the line passing through C alpha c with the slope of m is tangent to it. What does that mean? It touches the circle at the curve only at that point C. Only there. Doesn't touch it anywhere else. Okay? At least for in a region around C. That's an interval around C. Okay? That slope is the slope of the tangent line. Okay? Of the graph at C alpha c. And the slope of the tangent line to the graph at C, at the point C alpha c, is also called the slope of the graph of F at x equals c. So we don't just always say tangent line, though that's what we're talking about. We say that's the slope of the graph. That's how the graph is changing. The instantaneous change at that point. Slope of the graph. All right, here's example 1. And if you're following in the book, top of page 102. To find the slope of this graph here, oh boy, that's going to be a hard one, isn't it? Okay. F of 2x minus 3. When c is equal to 2, that's the x value, c is equal to 2, you can apply the definition of slope of a tangent line. Does anyone want to hazard a guess of what the slope of that's going to be? You don't have to, but I just wondered if you... Anybody? Okay, don't worry about it. Okay. So, let's do what they tell you to. F of... Let me get my pen set up. Okay. F of... We're doing it, c is equal to 2, so it's x equal 2 plus delta x minus alpha of 2 divided by delta x. That's what we were doing, right? You recognize that? That's the slope of the secant line. This is, and you're going to let the limit as that approaches 0. So this would be, what is f of 2 plus delta x when this is your f? Please tell me you can do that. Everywhere you see an x here, put in a 2 plus delta x there. What would that be? It's not that hard. You start with a 2, and then instead of x you put 2 plus delta x minus, now everywhere you see an x up here, you put a 2 in. Okay? You remember how to do that? What would that be? Anybody? Second? You may have said it right. Okay. Oh, wait, no, okay. Yeah, you're on multiply. I'm still doing this thing. This is that part. We need to put that part. What is alpha of 2?
F of 2.
Yeah.
4x minus 6.
No, f of 2. 4 minus 3, which is, come back. I didn't mean to be rude to you. There we go, okay. 4 minus 3 is 1, all right. And that's divided by delta x. So now let's do the math on it, which you were starting to do. 4 plus 2 delta x, that's what you were doing, wasn't it? Minus 1. Okay, what would that be? Oh, over delta x, right? That would be 3 plus 2 delta x over delta x. Okay?
x cancel.
Say again?
The delta x cancel.
I can't hear.
The delta x cancel out. The top and bottom.
Okay, I was just looking at that. No, it can't because this is done. Now, I'm doing something really stupidly wrong here, and I can't quite see what it is. Oh, I can't believe you let me get away with that. Wait a minute. We had a minus 3 here. It's 2 times that minus 3. Okay. Back off, Jack. Okay. I didn't finish the problem up here. The f of 2 plus delta x is 2 times this thing minus 3. I forgot the minus 3 there. And then we do the minus, what do we say that was? That was a 1, wasn't it? Yeah, that was a 1, minus 1. Ha! Now this is coming out a lot better. Whoa, wrong one. Okay. Let me erase this mess. And this mess. I can't believe y'all let me do that. Just sat there and let me get it. Okay. So let's figure out what this is. This is 4 plus delta x minus 3 minus 1 over, wait a minute, I didn't do that right either. 2 delta x. I forgot. 4 plus 2 delta x minus 3 minus 1. And that would, and this is over delta x. This is an easy problem, by the way, and I'm botching it up like crazy. Here's 4 minus 4. I guess it's 0. So we have 2 delta x over delta x. And what is that? 2. And the limit of 2 as delta x goes to 0 is 2. All right. This was the easy one, by the way. I just really messed up the doing of it. Okay? Now, I thought someone would look at this and say, wait a minute, I know what that is. What kind of function is that? It's a binomial, you're absolutely right. What's its degree? 1. What do we call first degree equations? They have a special little name. Say again?
Linear.
Linear, exactly. So this is the graph of the line. And what can you tell me about that line? That tells you something. Y-intercept, which I'm really not interested in. Well, what does this tell you?
Slope.
The slope! The slope of this line is 2. Guess what? We just found out the slope of the tangent line, which, of course, tangent line of a line is the line itself. Okay? And that's 2. We knew that. Okay? We knew that slope was 2. No matter what C we would have chosen, we would have still come up with the tangent line equal 2. The slope of the tangent line equal 2. You see that? Because if you draw a line, 2x minus 3, something like that, the slope at this point is that. The slope at this point is that. The tangent at this point is that. They're all along the same line. They all have the same slope of 2. And we've just verified it. This was the easy one. Okay, sorry about that. Okay, I get going too fast. Let me erase this and see what they do next. They did the same thing I was doing, but I just didn't pay attention to them. 2 times this, that, and that would be 2 times 2. You see, you just plug in this for x here, and this for x there. So this gives you 4 plus 2x minus 3 minus 4 plus 3. Okay? And now you see the 4's go out, the 3's go out, and you're left with a 2 delta x over delta x. The limit of that, the delta x divide out, and that leaves you 2. The limit of 2 as x approaches delta, as delta x approaches 0, is 2. There's your limit. There's your slope of your line, 2. You could have looked at it and told that was the slope of the line. Make sense? All right. Now, here's something we didn't quite do here. Well, we did too, in a sense. When you plug 2 in here, we've got 1. So that meant the point on this line was 2, 1. Okay? X equal 2, y is equal to 1. You got that right here, but they didn't show it here. But we did. So that's why they say the slope of f at c, f of c, the f of c, when c is 2, f of c was 1. So at 2, 1 is m equal 2, as shown in this figure. Okay? Notice that the limit definition of slope f agrees with the definition of the slope of a line. And that's a line. The slope is 2. Okay? So, yeah, that one's pretty obvious. The tangent line here is the line itself, because that's a line. It's not a curve, it's a line. So the tangent line is the line. Okay. Your change of y, delta y was 2. Change of x, 1. 2 over 1 is 2. The slope is 2. Every way you want to calculate it. All right. Okay. Looks like they're skipping example 2, so let's go back and us do example 2, and maybe we'll do a little bit better job on it. Okay? Let's do example 2. Find the slopes of the tangent lines to the graph of f of x is equal to x squared plus 1 at the points 0, 1 and negative 1, 2. Okay. Now, cynic that I am, I don't want to take your word for this. Is the point 0, 1 really on that curve? What happens if you plug in a 0 for the x? What's your y? 1, right? When you put 0 in for x, the y value is 1. Yeah, that one works. How about this one? When I plug a negative 1 in for x, what does that give you? 2. Yeah, so that one works too. So both of those points are on the curve. Okay? We want to know what the slopes of the tangent lines are at those 2 points. So how would we do that? What is so far our only definition of slope of a tangent line? The limit as x approaches, well, it's delta x approaches 0 of tell me. F of x plus delta x. Now, we already know what our x is. Our x for the first one is 0, so let's plug in a 0 for that one, okay? So this is just going to be f of delta x, right? 0 plus delta x is delta x minus f of 0, right? F of 0 plus delta x minus f of 0. That's our formula, right? All divided by delta x. Okay, so we got to plug that in now. So what's the f of your delta x in? Plug in delta x everywhere you see an x here. Can you? Put a delta x in everywhere you see an x there. What would that give you? Delta x squared plus 1, right? Agreed? Okay. Minus, and what's f of 0? We've already done it once. 1. Okay. And that's divided by delta x. seems like we're missing something here. Oh, they're doing the generic one, not the individual one. I don't know why they did it before. Let's go back and do the generic, okay? Because I knew I wasn't coming up. It should still give you the same thing, and indeed it would, but they're doing it more generically, okay? They're not doing the individual points. They're doing 1 point for both of them, and they're just saying let x equal c. So then the slope at c, alpha c, they're going back to that form, would be the limit as delta x is approaching 0 of f of c plus delta x minus alpha of c. We'll go back in and plug in 0 later. I was doing it right off the top. Over delta x, right? So let's carry it through. Gory detail this time. This will be the limit as delta x is approaching 0 of, and what is alpha c plus delta x? What you've got in parentheses here, you put instead of your x. So that would be c plus delta x squared plus 1, right? Plugging in, right? You're just plugging this in for your x. Do you see that? I don't know. When I try to do it on the board because then my pen shows up and I can see what I'm pointing at for people who are not here, but I'm not sure if I see here. F of this thing means you take everywhere you see an x here, you plug this in instead of the x. So this would be c plus delta x squared plus 1, right? Okay, now let's do the same thing for the second part, only here we're going to plug in c. That's yes in Spanish, right? So let's do c. What happens if you plug a c in where you have x here? Instead of x here, you plug in a c. What would that give you? Plug in a c. C squared plus 1. Minus, and I'm going to put it in parentheses for now, minus c squared plus 1. Y'all okay with that? Feel like a dentist pulling teeth up here, okay? Over delta x. Okay? So let's do this. Square this binomial. The limit as delta x is approaching 0, square c plus delta x. What do you get? Know how to do that? Please say yes. Somebody help me. There's two ways you can do it. There's a little formula that tells you how to do it, or you can do it by foiling. I don't care which way you want to do it. Formula or foiling? Second? I can't hear. Well, choose one. Anybody. Does anyone know the little formula? If you don't, we better foil. Agreed? Huh? You know what the formula is? Oh, foil. Okay, let's go with foil. So that is c plus delta x. To square something is to multiply it by itself, right? Okay? So let's do the foiling. First is c squared. Outer is plus c delta x. Inner is plus c delta x. And last is plus delta x squared. It's not delta x squared, it's delta x squared. And when you add these together, you get c squared plus 2c delta x plus delta x squared. And that works anytime you square a binomial. Square the first, that's the little formula, twice the product of the two, and then square the last. So that's the formula. So that would be c squared plus 2c delta x plus delta x squared minus, now let's do this one. Distribute the minus sign, minus c squared minus 1. Buy that? Oh, I've done it again. Wait. You let me get away with it again. I keep forgetting that. That was just this part. You have a plus 1 here. That's the second part of this. F of this is that thing squared plus 1. Okay. And then do your minus c squared minus 1. Okay. And then divide this by delta x. Whew. Now, notice what we got in our numerator. A c squared minus c squared is 0. Right? And a plus 1 minus 1 is 0. So all we've got left in the numerator is the limit as delta x is approaching 0. Okay. Let's do a timeout again. Sorry about this. Maybe I should have said this to begin with to make it more familiar to you. First thing we might want to do here is just plug it in, right? If you plugged in delta x equals 0 here, that would give you f of c minus f of c, which would be 0. And down here you get a 0. A 0 over 0 is an indeterminate form, so now we carry it out. Okay. So we've got this. We've subtracted out what we can, and you have a 2c delta x plus delta x squared over a delta x. That's an ugly delta. Okay? Now, you tell me, what can we do to that numerator to simplify it a little bit? Factor out a delta x. Sounds like a winner to me. Okay, so that's the limit as delta x is approaching 0 of a delta x in the numerator, and what would be left when you factor it out? 2c plus delta x, right? And you divide that by a delta x. The delta x's go out. Look at that. We got rid of that 0 in the denominator. So now we can plug it in again. And since we've lost these, when you plug in the delta x of 0 here, what do you get? 2c. Okay, or not 2c. No, okay, 2c is your slope. The slope of the tangent line for any old function like this would be 2c. So, in the first problem, c is 0, so the slope in the first one, m at 0 is going to be 0. 2 times 0 is 0. Over here, m at, I really should say negative 1, 2. That would be 2 times negative 1 is 2, negative 2. Perfect. We just found our two slopes. The way I was going to do it, we'd have also found them, but it may have been, you may have thought there was a trick there. We've done it generically. Any c you put in there, that's going to be the slope, 2 times whatever that c is. Okay? So let's look and see what they got in the book. They got 2c as the slope. Plug in 0, you get 0. Plug in negative 1, you get negative 2. Now, I don't want to draw the graph for people at home. You ought to be here if you want to see the graph. So I'm going to try to get the book, if I can hold it up that far. This is a parabola. Vertical displacement of 1. Good old standard parabola there. At 0, 0, your slope sure enough is 0. Okay? And at 0, 1, the slope is 0. At negative 1, 2, the slope seems to be downhill, pretty sharp. That's a -2 slope, and it is. I can't hold it up any longer. Okay. So sure enough, that seems correct. Now we get to the next part. Any questions on that? It wasn't in the book. I mean, it wasn't on the slide set, but we did it. Okay. Now they introduce something else here. The definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. Because a vertical tangent line, your rise is whatever you want it to be, but what's your run? Vertical tangent line. Rise could go from here to here. That would be some change of y here. What's your change of x? 0. That's not an indeterminate form. That's an undefined form. So the vertical for vertical tangent lines use the following definition. Well, okay, they're going to go into this. If f is continuous at c, then delta x approaching 0, alpha c plus delta x minus alpha c, for delta x going to 0. This could be any value in the world over 0. That's going to be infinity. Or it's going to be negative infinity. Who knows? Is that going up or is it going down? Vertical line, which way is it going? Can you tell? Oh, you think it's going up? How can you tell it's not going down? It's still a vertical line, isn't it? You can't tell. So therefore, why put infinities there? Why don't you say does not exist? Does not exist. Meaning it's a vertical tangent line. Then the vertical line x equals c passing through c, alpha c, is a vertical tangent line to the graph of f, which means the slope doesn't exist. So here is one such as that. See this going up this way, and then going like this. The tangent line here crossing only at that point there actually crosses the curve there, but is vertical. The slope of the tangent line is undefined. It has no slope, it has an undefined slope. It's either going positive infinity or negative infinity, you can't tell which. Undefined. Okay. Now, by the way, I don't know if any of you will ever run into this. This is very close to what they call a logistic curve. They use this a lot when they're talking about spreading of disease. Down here in a population, if one person gets the disease and passes it to another, the increase is pretty slow at first until a good number of people have gotten the disease, and then they're infecting lots more people, and the slope is going up close to infinite at some point. But then after a while, almost everybody's had the disease, so fewer people are getting it, so the rate of increase, but the number of people who have the disease, and what you're approaching here is the population. Everybody's been exposed, everybody's had it. Almost. It may just approach that line and never reach it. Maybe one or two people that just didn't take it. But that is that. Now, yes?
So the vertical tangent line would be, if like the line with the population, the vertical tangent line would be like the amount of time.
The curve here is measuring the number of people who had the disease. The slope is the rate at which that disease is spread. And right there is almost an infinite rate. Yeah, that's the fastest rate is when almost the same number of people have had it as not had it. That's going to be when it's spread the fastest. Now, if you think, I'm not going into medicine, any of you think you might be dealing with computers in your lifetime? Oh, you think so? Okay, all right. Do computers get viruses? Yes, they do, and they spread like this. If you can stop them down here, you may have a chance. If they get up to here, Katie barred the door, okay? It's pretty serious. And that's why they call them viruses. They act just like diseases, okay? All right, when the domain of F is a closed interval, A to B, you can extend the definition of a vertical tangent line to include the endpoints by considering continuity and limits from the left for x equal A and from the right for x equal B. But you don't have the whole thing. You have to just have one-sided limits there. anything in between two-sided limits. Okay. Now we're ready for derivative of a function. Okay? The limit used to define the slope of a tangent line is also used to define one of the two fundamental operations in calculus, differentiation. If it looks familiar, it is the same thing. So the definition of derivative of a function is the same as the definition of the slope of a tangent line. Derivative of a function, now here's a new notation, f prime of x. That means first derivative of f at the value x. Okay? As the limit, if your delta x is approaching 0, of f of x plus delta x minus f of x divided by delta x. There it is. Provided that limit exists. Now, if that limit doesn't exist, there is no first derivative. Okay. For all x's for which this limit does exist, f prime is a function of the same variable x. Okay? Get used to it. You're going to be seeing f primes a lot. Okay? And this is called a prime notation. There are different notations. We're going to talk about those fairly shortly, I think. At some point we will. Be sure you see that the derivative of a function is also a function of x, is also a function of x. They just said it there. They're saying it now. This new function gives the slope of the tangent line to the graph at any point x alpha of x, not just at some c alpha c, at any point x alpha of x, provided that the graph has a tangent line at those points. Derivative can also be used to determine, and this is another thing, the instantaneous rate of change, or simply the rate of change, one variable with respect to another. Okay? This is where we're getting into velocities, accelerations, those kinds of things, instantaneous velocity. This process of finding the derivative of a function is called differentiation. A function is differentiable at x when its derivative does exist at x, and is differentiable on an open interval a to b when it's differentiable at every point in that interval a to b. Sort of nomenclature right now. Very similar to what we're just doing. Basically identical to what we're just doing. In addition to f prime of x, which is read f prime of x, there are other notations used to denote the derivative of y is equal to f of x. And here are some of the most common. F prime, of course. Now, let's go back to your difference quotient. Remember that? The difference quotient was, remember, it was f of x plus delta x minus f of x. What is f of x? Someone that was in pre-calculus? Most important thing to remember in pre-calculus, what's f of x? Y. Why not? Okay, so this is, you could say delta y over delta x. So this thing was divided by delta x, remember? So this is delta y over delta x. Well, guess what? As the deltas get smaller and smaller and smaller, the limit as they go infinitesimal is dy over dx. The d just takes the place of the delta. Okay? Now, the other way you can express that is the change of what is y, f of x, so df dx. Now, that's sometimes written in quotes like that. Other times you just say df dx, where f is a function of x, but remember f of x is y. So these are the same forms. Oh, I skipped one. We can sometimes call y prime, because just like this is df dx, this is dy dx, that's f prime, this is y prime. So we use these same notations, different notations to mean the same thing. And then this is sort of a little bit different kind that you'll use in upper level courses probably. Capital D, which means the differential operator. That's this operator here, the d by d. Okay. I'll go over that in a minute. Wow, are you from India or Pakistan or somewhere like that? Huh? India. Okay. And I'm going to make a little bit of fun of an Indian accent. Are you going to be offended? Okay. I tutored, they're good friends of ours, and I tutored all three boys, but the older boy especially. He went back and actually studied computer engineering in India, and then came back but I was helping them because they have big tests over there at the end. You have to pass or the whole thing's wasted. And when I was tutoring him in calculus, and he was confusing the mud out of me because when I wasn't understanding what he was saying. When he said this, here's how I said it. Give me the X. He said it so fast I didn't know what in the world he was saying. But he was saying d by dx. That's what this C stands for. But he said d by dx. D by dx. I went, what? What are you saying? And finally I understood that that's what he was saying. D by dx of y. D by dx of alpha. I went, what? Okay. So, sorry. Just always when I see this notation, I think of Samuel. Okay. All right. This notation, dy dx, is read as the derivative of y with respect to x. D by dx. Okay. D by dx of y. Okay. Or simply dy dx. Now you say it as if it's a comma, and it really isn't a division. That looks like a division. That's an operator. D by dx is the operator operating on y. You're taking the derivative of y. Okay. So, this notation, and by the way, this is called the Leibniz notation. You remember the other guy, the German guy who developed calculus? He used this notation. They make fun of Newton. Newton used this notation. When he was taking the derivative of y, he just put a dot over it. Okay? And they called that the dot notation, and other people made fun of it and called it the fly speck notation. Because paper wasn't really pretty white like it is today. It was sort of rugged. And a fly speck on the paper you might think is a derivative, okay? And it wasn't. It was just a blot in the paper, okay? So the Leibniz notation stuck. The dot notation didn't. In fact, in many later years, I remember they always used the dot for d by dt and the prime for d by dx. That just came over time, but they don't use that much anymore. So this is your derivative notation. The change of y with change of x, infinitesimal change, dy dx is equal to the limit as delta x approaches 0 of delta y over delta x, which is what I was saying before. This is simply change of y over change of x. So that's where this comes from. This is the shorter note. This just takes more effort to write, and I'm lazy. So I kind of like this, or even better, y prime. That's just so easy to write. That means first derivative of the change of your y with change of x. Your slope at a point. Now, are we running out of time? No, we've got time. Was someone saying something? Thought I heard someone say something. Huh? Oh, okay. I can't hear. So. Second? I'm not hearing you. I Oh, you're thinking you're going to do it?
That's what you said. So, yeah.
Oh, no. Wait, okay. Slap yourself. I think you're dreaming. Because okay, no, I'm sorry. No, that is for you to work over this weekend. That's why I give you the whole week. You know. No, we got to take advantage of all the time we got. It was a good effort, though. Sort of. Okay. All right. Example 3. To find the derivative of f of x equal x cubed plus 2x. All right, we got to go back and use the definition. Remember this definition? Okay? We got to go through and do all that. So let's do it. To it. Okay? That's going to be the limit as delta x approaches 0 of, and what is f of x plus delta x? Plugged into this. Everywhere you see an x here, plug in x plus delta x. So what would that give you? X plus delta x cubed, right? Plus 2 times x plus delta x. Okay? Minus, and what's your f of x? X cubed plus 2x. Okay, and that's divided by delta x. All right, here we go, folks. there was a fairly easy little formula for squaring a binomial. There is an easier formula for cubing. One way you can do it was multiply x plus delta x times x plus delta x times x plus delta x. If you want to take the time to do that, you can. But has anyone ever heard of Pascal's triangle? Okay, heard of it. Let me write it down for you. Okay? And there is a reason for this. You start with a 1 at the top. And then you put a 1 on either side of it. And then you put a 1 on the outside of those. But you got to put something in the middle. So add these two 1s together and you get a 2. Okay? Then put a 1 on the outside, 1 on the outside. Add these two together and you get a 3. Add these two together and you get a 3. And then put a 1 on the outside, a 1 on the outside. Add these two together, you get a 4, 6, 4. Want to do one more? Sure. 5, 10, 10, 5, 1. Okay. Now why did I do that? This is X. Let me just make it a little simple. A plus B to the 0th power. What is anything to the 0th power? 1. Okay, there's the 1. This is A plus B to the 1st power. And what is something to the 1st power? A plus B. So there's your coefficients. There's the 1. The coefficient of A is 1. The coefficient of B is 1. All right? These are the coefficients of this thing. Okay? The first one is actually that. What is A plus B? A plus B squared. We just did that a short while ago. Anyone remember? I gave you a little rule. A squared plus 2AB plus B squared. What are your coefficients? 1, 2, 1. Look at that, folks. Anyone tell me what A plus B cubed might be? A cubed plus what? Okay. This coefficient, 3. Now, what we're doing is reducing our A's by 1. Does that give you A squared? But increase B by 1, B. Then the next coefficient, plus 3. Decrease A by 1, that would be A. Increase B by 1, B squared. The last coefficient, plus 1. I'll write 1, I don't need to. And then increase A by 1, that's A to the 0, that's 1. B cubed. There we have this is called the binomial theorem. Pascal's triangle shows you how it works. Okay? That's the easy way. The theorem actually is a lot longer. But this is what something cubed is. So instead of A, we're going to put our x's. Instead of B, we're going to put delta x's. Okay? Can I erase Pascal's triangle? Because I don't have room for it. Okay for it? Everybody got it? Can I erase? Okay, too late now. Okay, never mind. I'm just kidding. Okay. Got to speak up or forever hold your peace, you know. And we don't need the 0s and the 1s and the 2s. We know those. But let's leave that one there for now. Okay? So, what is this thing cubed? Be the limit as delta x is approaching 0 of, say again, x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. All right, that's that first term. Okay, second term will be plus, distribute, 2x distribute, 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 plus 2 delta x. Okay, next term, just distribute the minus sign, you get minus x cubed minus 2x. Divide all that by delta x. All right, and then magic happens, doesn't it? Okay, here we have an x cubed, and there we have a minus x cubed. Those disappear. Here we have a plus 2x, there we have a minus 2x, and those disappear. They add to 0, right? Now what do we have left? The limit as delta x is approaching 0 of 3, because I'm running out of room, can we do something else first? Let's look a little bit ahead. See, I like to skip some steps myself. This term has a, okay, this term has a delta x in it. This term actually has 2 of them. This has 3 of them. That one's gone. That has a delta x. The other 2 are gone. So guess what we can do? Factor out a delta x out of every term. So this will give you a delta x, now this is in the numerator, times what? 3x squared plus 3x, and we only factored 1 out, so we're left with 1 delta x. And then the next one, we factored 1 out, so we're left with 2, so that's delta x squared, okay, plus 2, right, because we factored out the delta x. All right, and we'll divide this by delta x, and then this is where the real magic happens. The delta x's go out because they become 1, right? So now we can plug in. If you plug a 0 in for your delta x, that goes to 0, and that goes to 0, doesn't it? So now we're left with, when you take the limit, you get 3x squared plus 2. All right, that's what we got. Let's see what the book got. 3x squared plus 2. Good for them. I'm so proud of them. Okay? See it? Aren't these limits fun? Yes. Okay. So I'm going to erase this. Is it all right too? Everybody got it? Or you still need it a little longer? Do I need to take this box off? Is that blocking something? Okay. Okay, sorry about that. Ooh, give out. In probably a day or so y'all are going to hate me because I drug you through all this limit stuff. Then I'm going to show you the easy way to do it. Can't wait. Okay, I don't like these limit things either, but this shows how we got them. Okay, everybody got it? Still getting? Got it? Okay, all right, to erase. Speak now or forever. Okay. All right, here they're going to show the same thing here. This will be the limit of alpha of x plus delta x will be x plus delta x cubed plus 2 times x plus delta x. That's that part minus alpha of x, which is simply that part. Okay, divided by delta x. And this is doing the same thing we did, only a little bit neater maybe. And then from nowhere, they came up with this formula here. I'll show you where you got it from Pascal's triangle. By the way, since I mentioned the name Pascal, guess what? He's legitimate for a paper topic. And so is his triangle. How did he develop that? Why did he develop that? Or how is it used beyond what we said? There's lots of uses, okay? And Pascal was a pretty interesting character, too. He did a lot of the early work in statistics. You know why he did? Because he was really interested in applications to medicine and all that. No, because he liked to gamble. And he found out statistics gave him an edge to gambling. So, oh, shucks, have I just ruined your icon? No, never mind. Okay. I'm sort of exaggerating a little bit. The first really wonderful applied statistician. You know who that was? These other guys just use it mostly for gambling purposes. Florence Nightingale. She took what they used in their calculating odds and all that kind of stuff, applied it to nursing and said, look you guys, look how many infections we're getting. If we do this, we're going to, you know, she used statistics to sanitize hospitals, to improve medicine big time. First, really, in my mind, great applied statistician, Florence Nightingale. Never heard her mention much in the top of the statistics she was. She's the mother of nursing, don't quite get that. So, same thing we did. They got all this stuff, and then they distributed this, okay, and then they distributed the minus sign just like we did, divided by delta x. And let's see, are they going to show it or just, yeah, they don't show it. The x cubed and minus x cubed go away, and the 2x and minus 2x go away. These are the terms that are left. I skipped this step, sorry about that, but I was just running out of room. They write smaller, so they have more room. And they notice here there's a delta x in every term, so they factored it out, and once they factored it out, it got rid of the denominator. Now you're ready to substitute. Plug it in, 3x squared, plug in a delta x going to 0. In this term, that goes to 0. In this term, it goes to 0. And that just gives you a 3x squared plus 2. Oh, they drag it out a little further. Okay. Then they take the limit and get 3x squared plus 2. All right. Any questions? Same thing we did. All right. We've done, and by the way, I did mention, example 3 was also, you can see larsongcalculus.com for an interactive version of that type of an example, the one we just did, that one, okay? And boy, they go into gory detail, and you can interact with it, okay? Now, they're skipping examples 4 and 5, so let's back off and do 4 and 5. How are we? Oh, we got plenty of time. Good. Before you get to start on your test. Okay. All right. Good deal. Example 4. Find f prime of x. This is what we're looking for. When f of x is equal to the square root of x. Okay? Do I hear a big boo hiss? Because this is a little bit harder than the other one, but it's still doable. Okay. And then find the slopes of the graph of f at the points 1, 1 and 4, 2. Before we go any further, let's make sure that 1, 1 is on this graph. Is it? Plug the 1 in for x. What's square root of 1? 1. Yep, that worked. Square root of 4? 2. Yep, that works too. So those 2 points are on the curve. So we will come back and do that too. And discuss the behavior of f at 0, 0. Is that a point on it too? Yeah. Yep. Good deal. All right, but what we first have to do is find what f of x is, f prime of x is. And what's the definition? For right now, starts with those 3 little letters. The limit, as delta x is approaching 0, of f of x plus delta x, our favorite, minus f of x divided by delta x. Okay, that's what it is. Now, we'll stay with square roots now. Later, you'll find me saying I don't like to take derivatives of radicals, and I don't. But since we're using the formula now, we'll stay with it. So what will this be? What's that defined as? Starts with the same 3 letters. The limit, as delta x is approaching 0, of, what is f of x plus delta x? Tell me. Here's your function f. It does that to it. So what would it be? Someone tell me, huh? The square root of x plus delta x minus the square root of x all over delta x. Now, I have forgotten the last couple of times, even though I've gone back and said it. If you were to try to plug in at this point, what would you get? If this is going to 0, you'd have square root of x minus square root of x, which is 0 over 0, okay? Indeterminate form. So what can we do to that to make it more palatable? Yes, yes, yes. Multiply by the conjugate of the numerator. Usually you do it of the denominator. What is the conjugate of the numerator? Plus the square root of x. But if you multiply the numerator by that, you got to be democratic about it and multiply the denominator by the same thing. Square root of x plus delta x plus the square root of x. Okay? So, let's sock it to that numerator. Okay, let me write down the first three letters. The limit as delta x is approaching 0. Now let's do our FOIL here, folks. What would that give us? X plus delta x. You multiply the square root by the square root, you get what's inside. Okay? And then the innards and the outards. Yes, exactly. So those disappear. So you then have the last. And what's that? Minus x. Okay? All over delta x. Is that right? Oh, no. You're trying to get me to do something wrong, weren't you? Okay? It's delta x times the square root of x plus delta x plus the square root of x. We had to multiply that, remember? But what do you notice about your numerator now? X minus x goes to 0. You're only left with the limit as delta x is approaching 0 of delta x over delta x times, yes, you want to just cancel them here? Yeah, let's do it. That just leaves a 1 there, okay? Now, oh, yeah, okay. I'm glad you could skip that step because I didn't want to write it again. I knew you wanted to see me write it again, but no. Okay, so at this point where you have a 1 over this thing, at this point we can plug it in, right? So put a delta x going to 0 here, what do you get? Square root of x plus square root of x, which is, I'm sorry, I meant to open the door for you. What does that give you? 2 times the square root of x, right? If delta x is going to 0, this is square root of x plus square root of x, right? Square root of x plus 0 is square root of x. I'm sorry. X plus 0 is x, right? So that would be square root of x plus the square root of x, right? I'm sorry? Okay. We're doing the limit as delta x is approaching 0. Okay? So let me write that out here. Maybe this will help. As delta x is approaching 0 of what we had left over was a 1 over the square root of x plus delta x plus the square root of x. Okay? It'll come back, I hope. Yes, here we go. So, that's what we had left over from here, right? Those went away, these went away, everything went away except 1 in the numerator, this is nothing. Now let's do our limit. We tried to before and we wound up indeterminate, 0 over 0. Let's try it again. Here when we take the limit and put delta x going to 0, that goes to 0, right? So you have 1 over the square root of x plus the square root of x. That's 2 square root of x, right? Okay. So this will be, when I take that limit, it will be 1 over 2 times the square root of x. Okay? Now, that, by the way, is your answer here. If you notice in the text, that's the answer, the first part of the answer. That's f prime. That's your f prime of x. Now, I really want to do this, and it doesn't make any sense probably to you why I would do this. But what I want to do is express this in exponential notation. What is square root of x in exponents? X to the what exponent? Anyone remember? To the 1/2. The square root of x is the same as x to the 1/2. Got it? So what would this be then? This would be 1/2 times 1 over the square root of x, so that would be x to the minus 1/2. Okay. I just wanted to say that and do it for now. Later we'll come back and remember that. Here, it doesn't really matter. Okay. So, let's go on and do what the next thing it said. We found f prime. That was the hard part. Then find the slopes of the graph of f at points 1, 1. This point right here. We're looking for the slope. So the slope at 1, 1 would be what? Let's use this. Yeah, that would be 1/2. Just 1/2, wouldn't it? Because you plug x equal 1 in there. Square root of 1 is 1. So that would be 1/2. Buy that? Okay. Then we'll do the graph at the slope at 4, 2. And that would be what? 1/2 times 1 over 2 times, and what's square root of that times 2? So that is 1/4. All right, that wasn't too bad. It says, discuss the behavior of f at 0, 0. Well, what happens if you do that? M at 0, 0 would be, say again? Looks like a 5?
Undefined.
Huh?
Undefined?
Undefined. You're absolutely right. Undefined. Absolutely. Now, if you think about the graph of this function here, this is going to be a pretty low-scale graph, okay? Remember, that's not defined for x negative, so it's only going to be on the positive side. 0, 0 is certainly there, 1, 1 is certainly there, and 4, 2 is certainly there. Here's how the graph of that looks, right? I like to call that half of the sleeping parabola, right? Parabola on its side, sleeping, and just the top half of it. Can't use the bottom half because that wouldn't be a function anymore, would it? Okay, so that's it right there. That's the square root function. And guess what the slope is? The slope here was 1. The slope here was, 1/2. The slope here was 1/4. The slope here would be greater and greater and greater. Guess what the slope is right at 0, 0? Vertical. Undefined tangent line there. So that's why this m at 0, 0 is undefined. That's a vertical slope because that's going up. Just like that, the slope would be vertical at the vertex. Okay? Make sense? Please say yes. All right, good deal. All right. Now, can I erase it? Anyone still writing? I'll leave it up if you need it. Everybody got it? Okay. All right. Let's do example 5. Do we have time? Maybe. Let's give it our best shot. And by the way, this one you can also see larsoncalculus.com for an interactive version of this type of example. Find the derivative with respect to t for the function y is equal to 2 over t. Y is equal to 2 over t. And in a later time, not too many weeks away, I will be saying I don't like to take derivatives of variables in the denominators. And we'll have you do something else with it. But right now it's going to be okay. So what would be the derivative of that function? What's the definition? The limit as delta t is approaching 0 of have an offset, that's it, f of, or you could say y. You want to say y? Why not? Y of okay, it's not x anymore, it's t. T plus delta t minus y of t, right? Divided by delta t, as delta t is approaching 0, right? So what's y of, that's a pretty ugly y, isn't it? Let's see if I can clean it up just a little bit more. Okay, I cleaned it up too much, okay. Okay. So y of t plus delta t would be what? The limit as delta t is approaching 0 of, it'll come back, okay. Everywhere you, this is a function of t, everywhere you see a t, put a c plus delta t. So what would this be? Help me. The y function starts off with a 2 and divides by whatever's in the parentheses. And what would that be? T plus delta t minus, say again, 2 over t. 2 for t and t for 2. Never mind, okay. Over delta t. Now, Teresa, is this looking familiar? Yeah. What would you do with that numerator? Say again? You're subtracting two fractional forms. How do you subtract fractions? Common denominator. What would be the common denominator? The product of the two. So to get this to be the common denominator, we'd have to multiply by t, right? Because if you multiply the denominator by t, you got to multiply the numerator by t as well to be nice and democratic about it, right? Okay? And to get this denominator to be the common one, what you have to multiply by? T plus delta t. But if you multiply the denominator of that, what did you better do? Multiply the numerator by t plus delta t as well. Because these two entities, t over t is 1, so you have to change that. And this over this is 1, so you haven't changed that either. You just change the way they look. All right, so let's do that. In your numerator, we now have a common denominator of t times t plus delta t. I don't recommend that you multiply those through. I don't think it'll be helpful. In your numerator of the numerator, you have a 2t minus, and then 2 times t would be 2t, and minus 2 times delta t is a minus 2 delta t. Is that okay to do it that way? I just didn't want to write everything again. The 2t is up here from there. This is minus 2 times t. That would be minus 2t. This is a minus 2 times delta t. Minus 2 times delta t. Right? Okay, and that's all over by delta t. Okay? But what do you see happens? Magic again. The 2t minus 2t is 0. Okay? A little bit more magic. This delta t can divide out that delta t. So now we can take a limit and let this delta t go to 0. Okay, and what would we get? In the numerator, you got a minus 2 over t times, and the delta t is going to 0, so it's t times t is t squared. In the denominator, you got a 1. So minus 2 over t squared. Let's see what the book got. Oh, look at that. Minus 2 over t squared. Good for them. Now, I told you I don't like taking the derivative of a variable in the denominator. Here's how I would have written this. I would have written this as 2 times t to the minus 1. Is that not the same thing? Okay. And then I don't like this either, so I would have written this as a minus 2 times t to the minus 2. Wouldn't that be the same thing? Okay. That's just for future reference. You don't have to worry about it now, but that's how I would write it. Okay? We'll see a reason for the madness later. All right. I guess we got time. Any questions on this before I erase? Okay, so people still writing. I'll let you write. Is this making sense? Okay. Are you following it? Okay. Any questions? Good time to ask. Always good to ask questions. Navy schools weren't the greatest thing in the world, but they did have one phrase that I thought was really good. And just about every instructor, I guess, had been drilled in them to say this. They'd say, there's no such thing as a dumb question. So don't be embarrassed that what you're going to ask is a dumb question. Except one. There is one. That's the question you don't ask. That's dumb. As soon as you ask it, it's not dumb anymore. But if you don't ask it, that's dumb. So no dumb questions in here unless you're not asking them. But any question you ask, by definition, is not a dumb question. Can I erase? I see no objection. Oh, you still writing? Okay. You got it. Everybody done? Okay. Huh? It will be. It'll be loaded sometime later this evening. Now, we have maybe 5 minutes, or do we? 4 minutes. Okay, let's at least introduce differentiability and continuity. The alternative limit form for a derivative is useful in investigating the relationship between differentiability and continuity. And here is the alternative form. F prime of c. See, before we said, it sounds like zipping up time, doesn't it? Let's go on to that. We'll pick up with this next time. Okay. Y'all aren't going to pay any attention anyway, are you? Okay. Now answer that question. Okay, we'll start at the top of page 1. Oh! I do have time to give you some homework exercises. I'm glad you reminded me. Okay, you can do 5. It's a Calc Chat. You can do 7. It's a Calc Chat. You can do any of the odds 9 through 13. They're all at Calc Chat. 11's a Calc View. You can do any of the odds 15 to 27. They're all at Calc Chat. 17's a Calc View. You can do any of the odds 29 to 35. They're at Calc Chat. 31's a Calc View. You can do any of the odds 37 to 41. They're all at Calc Chat. 37's a Calc View. I think you can do 43 or any of the odds 43 to 47. They're all at Calc Chat. I think you can probably do 49 and or 51. They're exploring concepts. They should be at Calc Chat. Using a tangent line, 53 is at Calc Chat. Working backwards, if you want to do that, is 55 or 57, both at Calc Chat. 57 is at Calc View. 59 should be at Calc Chat. 61 at Calc Chat. 63 is a graphical reasoning, as is 65. I think you can do those. Let's hang off there and we'll finish the rest of those later. Good deal. Have a good weekend. You got your test? Everybody? Good deal. It will be a great weekend. Calculus all weekend, right? Yes, how could it be getting any better than that? Okay.